Okay, we're on section 6, chapter 4. So section 5 was about sine, cosine graphs. So this section we're going to talk about the other 4 trig functions that we've been introduced to. We're going to concentrate on the tangent function. The other ones we'll talk about in general, but we won't talk about their transformations. They're basically the same, but it would take too much time to really get good at it, so I'd rather spend more time on getting the sine, cosine, and tangent worked out. So first we're going to introduce what the general shape of them is, and then we'll talk about transformations regarding the tangent function. So the other 4 functions are the tangent, the cosecant, the secant, and the cotangent. The cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. And the graphs for all these, well, the tangent and cotangent, very similar. The cosecant and secant are not very much similar to the sine and cosine at all. And basically what we can do is we can look at the definition of the other trig functions in terms of the 2 trig functions which we have already plotted. So we have a general idea of what the sine function looks like, and the cosine. They're essentially the same, except just shifted in the x direction. So we have the tangent, which is the sine over the cosine, cosecant 1 over the sine, secant 1 over the cosine, and the cotangent, cosine over the sine. And you'll see that I've got this other column that says does not exist when, and I've got this in terms of, not in terms of theta, but in terms of the other trig functions. So the tangent does not exist when the cosine of theta is 0, and that happens when theta equals pi over 2 or 3 pi over 2. So if you think about a unit circle, pi over 2 is the y-axis, the x value is 0, x value is the cosine. So the tangent does not exist at pi over 2 and 3 pi over 2, from 0 to 2 pi. Now the cosecant is 1 over the sine, and the sine of theta equals 0, which again will give us an undefined result when theta equals 0, pi, and also 2 pi. For the secant, it's the same. The secant has the same conditions under which it does not exist, because in the tangent the cosine is in the denominator and the secant the cosine is in the denominator. So the values of theta where the secant does not exist are theta equals pi over 2 and 3 pi over 2, and the cotangent of theta is undefined when the sine is 0, and the sine is 0 when theta equals 0, pi, 2 pi. So what we're going to have is vertical asymptotes at these values of theta for these functions, and those help guide the drawing of them. Also, for the tangent and cotangent, we've got this condition where the value is 0. So when the sine is 0, the cosine is 1. So when the sine is 0, we get a x-axis, we get an intercept. And the same thing's true here for the cotangent. When the cosine is 0, the sine is 1. So where that happens, you have an x-intercept. So we have vertical asymptotes and x-intercepts for the tangent and cotangent. For the secant, cosecant, we have some other ways of kind of guiding us on what they look like. Well, the main point is we have the vertical asymptotes. We also have a part where the sine of here, when the sine of theta equals 1, you have 1 over 1. So when the sine's 1, the cosecant's 1. When the cosine's 1, the secant's 1. You'll see what it does in a second. So as I just mentioned, the vertical asymptotes are critical for plotting these functions. The sine and the cosine can be evaluated at any value of theta, so there are no vertical asymptotes, but all of these have some place where the function does not exist. Now, in terms of sine and cosines, the amplitude and the period were pretty self-explanatory. It's a little more difficult for the secant, cosecant, tangent, cotangent. So, and also the period. The period for a sine and cosine was where we went through one complete oscillation. So we started at 0, went up to max, through 0, back through the minimum to there. So that was that distance was the period. Now, we look at the period. We can tell by when we have two vertical asymptotes. That's the period. The distance between two vertical asymptotes is a period. And the same is true so all of these periods can be related to the location of the vertical asymptotes. Now, as far as the amplitude is concerned, that tells you what the minimum value of it is. So if the amplitude is 1, then the minimum values are +1 and -1, and the function does not exist between -1 and +1. Whereas for, say, the amplitude were 2, the function does not exist between -2 and +2. And we can draw those as boundaries. So now, as far as the period of the amplitude of the tangent, depends how quickly the function value increases as you go through the x-intercept. So first we're going to talk about the tangent function. So what I have here is I have the red curve, which is the sine, and I have the blue curve, which is the cosine. And as you can see, the tangent is the sine divided by the cosine. So where the cosine is 0, we have a vertical asymptote. So you'll notice the blue curve, which is this cosine curve, I've drawn these vertical lines. So that's how you locate where the cosine goes to 0 when it crosses the x-axis. That is the same location that the tangent has a vertical asymptote. Now, in between those vertical asymptotes, right in the middle, you have the point where the sine of theta is 0. So you have 0 divided by the cosine of theta, which is 1. So you get 0 over 1, and therefore we have an x-intercept there, and we'll have the same. You see the cosine goes to the sine goes to 0 there, the sine goes to there. So those are our x-intercepts. And then we've got these vertical asymptotes. So we're either going to come down, go through 0, and then go this way, or we're going to start at the bottom and move up. So the other key thing to remember is the tangent of pi over 4 is 1, and the tangent of negative pi over 4 is equal to -1. We know this is true because if you take that's the tangent of pi over 4 is the sine of pi over 4 divided by the cosine of pi over 4, and pi over 4 has the same trig function values for both the sine and the cosine. So you get something divided by itself as 1. So what I can do now is I can plot 1 unit to the, or halfway between this point and the vertical asymptote. That's going to be 3/4 of the distance between the two vertical asymptotes. So I've got a quarter of the way, I've got half the way, 3/4 of the way. So I'm going to look for about the midpoint here, and I'm going to go up to 1. And I'll go halfway between this intercept and the vertical asymptote, and I'll go -1. So it's about halfway, go down to -1. And then you've got the vertical asymptote. So we know the vertical asymptote has to come this direction. So I've got a point here, point there, point there, so I'm going to go in that direction. And it goes through there, and then it continues up. Now, it turns out that between every vertical asymptote you have the exact same looking function. So here I'm going to go halfway between the x-intercept and the vertical asymptote and go up to 1. Do the same thing, go halfway between here and the vertical asymptote, go down 1. You see here a -1, +1, and you just repeat over and over again. Now this distance between two vertical asymptotes, this is the period. So that's how the period, so they're vertical asymptotes, half the period of the function. In between the vertical asymptotes you have the midpoint. Now this point is 0 unless you have a vertical shift. If this was shifted vertically 1 unit, then this point would move to there. Everything would move up 1 value. If you have a shift of -2, this would move down to there. And these points here are going to be this, relatively speaking, the same distance from this midpoint between the vertical asymptotes. So that's what tangent function looks like. So let's do this one here. Go halfway between the x-intercept and the vertical asymptote. Go up 1 unit. Go over here halfway between the vertical asymptote and the x-intercept. Put that point, and then draw a function that looks like that. Just keeps repeating over and over again. Okay. Now, if you have, if you had an x-axis shift, then these vertical asymptotes would get shifted one way or the other. If the amplitude is something other than 1, then this still the x-axis crossing is still the same. But if it was 2 tangent of theta, then this point will get moved up to 2, and this point will get moved down to -2. So it shifts these points that are midway between the x-intercept for the function and the vertical asymptote. We'll come back and we'll talk about transformations for this one particular function. But first let's look at the other functions. So the cotangent is very similar, except what you have is the vertical asymptotes are now occurring when the sine is 0, because remember the cotangent of theta is the cosine of theta divided by the sine of theta. So we have vertical asymptotes when the sine of theta equals 0. So that's sine, this is the red curve is the sine, so we're going to have vertical asymptote here, vertical asymptote there, vertical asymptote there, so that's where the sine goes to 0, and you see the vertical lines. Likewise, when the cosine is 0, the sine will be either 1 or -1. So you'll either have 0 divided by 1 or 0 divided by -1, which is still 0. So at this point we have the x-intercepts where the cosine goes to 0. Now with the tangent, we started down here and went upward, but it turns out with the cotangent we go the opposite way. So we go halfway between the x-intercept and the vertical asymptote. We move up 1 unit. Here we're going down 1 unit for the tangent. Again, halfway between the x-intercept and the vertical asymptote, and we go down 1, and then you draw it in. So you see how similarly they look. And then you have the same thing over here. You go halfway up 1, halfway down 1. Draw it through like this. Notice that this, when it goes through the x-axis, it doesn't flatten out very much at all. It just pretty much goes straight through. Okay, so let's go over here, halfway up 1, halfway down 1. There's another vertical asymptote over here, which I didn't show. So again, you can see the period is the distance between two vertical asymptotes, any two vertical asymptotes. It's also the twice the distance between the x-intercepts. So we have one here, another one, you skip over that, you don't count that one. So the distance from here to here is the same as the distance from between the two vertical asymptotes. So that's why I said the cotangent and the tangent very similar. They're shifted a little bit from left to right, and they're also flipped, but they're the same basic kind of shape. Now the secant, remember the secant of theta is 1 over the cosine. So you'll have vertical asymptotes when the cosine of theta equals 0. So this, again, we have the red curve is the sine, the blue curve is the cosine. So notice where the blue curve crosses the x-axis, we've drawn these vertical lines in. The period is the distance between two vertical asymptotes. Now, I've also drawn these horizontal lines at 1 and -1. So because the sine and cosine functions oscillate between -1 and +1, the secant functions oscillate between, well, they don't oscillate, they go from positive infinity down to 1 back to positive infinity. And then when you go to the next half period, you go down here, because the secant is going to be 1 divided by this value, the cosine value, which is -1. 1 divided by -1 is -1. So these, let's put these in here. So we got the vertical asymptotes. That midpoint is 1. Then we go down here to -1. Then it'll be up to +1. Be over +1. Go down to -1. Up to +1. And then the function is going to come down here to 0. I mean to 1, and then loop back up again. And down here, it's going to come from -infinity. Come up to -1 and then loop around. You know, there are no values for theta where this goes to 0, so we never cross the x-axis. We actually never go between these lines, and they just alternate back and forth, above, below, above, below. And so the cosecant is very similar to the secant, just like the sine is very similar to the cosine. So you have here 1 over the sine of theta. So you have a vertical asymptote when the sine of theta equals 0. So you can see the sine of theta equals, this is the sine function, the red oscillating curve. So you see we have a vertical asymptote here, this point where the sine is 0. You have another vertical asymptote here where the sine is 0. When it crosses over here, you'll have a vertical asymptote. When it crosses here, you have a vertical asymptote. Now, notice this is 1 over the sine, so here's the sine. So the cosecant is going to be right here. Another thing you can think about is that, you know, where the cosine here matches up with the secant at that one point. They touch each other. So this one's touching the red curve, and then you go down here, touch the red curve, and you go down here, touch the red curve, red curve. And again, this one's going to go up like that, back up. This one's going to go down to -infinity. This goes down to -infinity. This one goes down. This one goes down. This one goes up. So if you look at the secant and the cosecant, you see if I took this green curve and just moved it pi over 2 to the left, I'm going to have the secant. So we just want you to know the general shape of cotangent, secant, and cosecant, but we're not going to do any transformations with them. Okay, so let's look at the tangent function. So it's very similar to what you had for sine and cosine. You're going to have some kind of amplitude a times the tangent of, say, a, small a, x minus b plus c, and this is plus or minus. So a is the amplitude. Which is not, it doesn't quite have the same meaning as for the, and I'm actually sure it's called the amplitude. I'm going to call it the amplitude. This plus or minus here is, that's going to be the x-axis reflection. A is related to the period. The period is 2 pi divided by a, just like normal. So we take that value. But, you know, what we did before was we factored out the a. So we had a times the quantity x minus b over a plus c. So b over a is the x shift, and c is the y shift. And I think that's it. So remember, this is the period. So I'm going to start off with we just know what the parent, we know what the parent function looks like. So let's say we change the inside of the tangent to, instead of bx, let's have it as equal to 2x. So what does that say? Well, we come over here, it says there's no horizontal vertical shift. There is a period that's different than 2 pi. So the period for this function is going to be 2 pi divided by a, which a is 2. So we get a period of pi. So what that means is we have vertical asymptotes every pi over 2 on x-axis. We also have the tangent of, yeah, I guess I really don't need to put, just need to show 2x or 2 theta. So that's a function, f of x equals tangent of 2 theta, or 2x. So the tangent of 0 is still going to be 0. So we're going to have an x-intercept at 0. We'll use that part, we'll use that location to help generate the curve. So, okay. And we're going to center this around the origin like we did. There were two options. We can have two periods to the right of the origin, or we can center it around the origin. So two periods would be, period is pi, so we go plus pi here, so that's pi. We go the same distance the other way, that's negative pi. Then we break it up into 2, it's pi over 2, negative pi over 2. You'd have pi over 4, 3 pi over 4, 3/4 pi, negative pi over 4, negative 3 pi over 4. Okay, now it says that we have vertical asymptotes every pi over 2, but we also have this intercept at 0. So that for this to be in the middle of two vertical asymptotes, I have to go from negative pi over 4 to positive pi over 4. That'll be a total distance of pi over 2. So I'm going to draw two vertical asymptotes, one here and one there. And once you get started, the rest of them are no big deal. So you see that 2 marks is pi over 2. So 1 to the next vertical asymptote is going to go here, 3 pi over 4, and I'll move that in a second. Then you go back to in this direction, and let's put one more. We'll put one more outside here. So if I were to draw a vertical asymptote, which would be at negative 5 pi over 4, and let's see about that, right? So if I extend this out like that, and do the same thing over here, so it's going to be slightly larger than 2 periods, but okay, so those are my vertical asymptotes. Notice I have this x-intercept right in between the vertical asymptotes, so I just repeat that. I got all these x-intercepts right between the vertical asymptotes. Now remember that we need 2 more points, and so we go halfway between the x-intercept and the vertical asymptote, and we go up 1 unit. So let's mark my y-axis here. So that's 1, it's 2, it's 3, negative 1, negative 2, negative 3. So we go halfway between here and there. I'm going to go up 1 unit. Halfway between here and here, go down 1 unit. And I can do that for all of them. So I'm going halfway up 1, halfway down 1, 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 and then you can draw the lines in. So you start here at negative infinity, going through that point, through the x-axis up here, and then they're all going to have similar behavior. Okay, so that's the first thing. Tangent of 2x, tangent of 2 theta. And let's just plot this thing just to show you it does work. So let me find my graphing program. Okay, so first we're going to set our minimum, which is going to be negative pi and positive pi, because we're going 1 period to the left and 1 period to the right. The maximums, we'll keep it at plus or minus 5. And then we will plot tangent 2x. And there you go. So if we look at the two, see they're very similar. Notice if you go here, so the vertical asymptote is going to be here at x equals, let's change the view so it's at multiples of pi. So at pi over 4 we have this vertical asymptote. So if you go halfway between the x-intercept and the vertical asymptote, which is about right here, you'll go up 1 and you'll do that point. So there's 1. And then you do the same thing, you go to the left halfway between 0 and the vertical asymptote, which is going to be about right here, and you go up, go down 1. So that's what those points correspond to. Okay, so let's see what we can do now. Let's say we have the tangent of negative x. So this is, because it's inside the argument, this negative represents a y-axis reflection. The period is going to be 2 pi over a. So let's go back to, I just realized something. this is plus or minus a. So if a is positive, then there's no reflection. If a is negative, then it's going to be a y-axis, but the magnitude is telling us how much the period changes. So I'm going to use the positive value here, positive part of a, to do the next one. So you get 2 pi divided by 1, which is 2 pi. So instead of going from 0 to pi, we're going to go from 0 to 2 pi and go from negative 2 pi to 0. That'll cover 2 full periods. Let's do it to the right of the axis. So in this case, I'm actually going to go 2 periods is 4 pi. So we'll go 4 pi out here. And then we go halfway, which is 2 pi. And that's 1 period. So then we cut that in half, it's pi. Cut that in half again, which is pi over 2. And this will be 3 pi over 2. This is our normal arrangement. Then you go halfway between 2 and 4, which is 3 pi. And 3 pi, 4 pi, 5 pi. This will be 5 pi over 2, and this will be 6 pi over 2, and then 7 pi over 2. So those are the values for the that help set the period. Here it's about to run out of power, so I have to plug that in. So but it's not going to take long, so I'm going to turn my recording off. Okay, there we go. Back in business. So remember, the vertical asymptotes are at every half a period. So half of 2 pi is pi. So we'll have, and you might say, okay, I'm going to draw a vertical asymptote here at pi, but remember we have the added restriction that the tangent of 0 is 0. So if I have negative 0, it's still 0. The tangent of 0 is 0. So that means that the first vertical asymptote is going to be here, pi over 2. They'll also be one at negative pi over 2. And then I can clone this thing, so half period, another half period, another half period, another half period. Again, halfway between the vertical asymptotes, it's 0. Now, what's going to happen here? We have a y-axis reflection. So what I'm going to do here is I'm going to clone this thing and show negative pi over 2 as well. So if you remember, the tangent function looks something like this. But if you have a y-axis reflection, this is going to move over here. So what will happen is it will go this way. Also, the other thing we were doing was we were helping get those 2 extra points. So go halfway between the x-intercept and the vertical asymptote. It's 1, except it's over on this side because it's y-axis reflection. So that's there. So we go halfway between, we go down 1, and then everything, just keep repeating this arrangement. Each half period you get exactly the same looking graph. And then once you have that, you can go ahead and draw these in, going down from the vertical asymptote through this guide point, going through the x-axis, going through this guide point, going down to negative infinity, and you'll see that same kind of deal. They're all going to look exactly the same. So let's pull up the graphing utility. So we're going to go from 0 to 4 pi. Period was 2 pi. We'll leave the y values the same, and it's the tangent of negative x. So there you go. You can see how they're now coming from positive infinity through the x-axis down to negative infinity. See, the first vertical asymptote is at negative or positive 0.5 pi, which is pi over 2. So that's this vertical asymptote. Notice how they come from positive infinity down through the intercept, and then they just repeat each other. So that's how the negative sign affects the function. Let's see what else we can do. Let's say we have 2 times tangent of x. So here I've got this multiplier, and so it's going to look exactly, well, it's going to have a very similar behavior to what I have down here, except I don't have the negative, so it'll, instead of coming down this way, it'll start low and go through 0 and come up. The difference is that this 2 here is going to double my y value. So instead of going halfway between the vertical asymptote and the x-intercept and go up 1, we'll go up 2. So it'll have much steeper rise. So let's just do that. We'll do, we'll center it just to alternate between the two approaches. So there's the 0. So what we would do is we'd go to the right 1 period. We go to the left 1 period. We break this up into half and a quarter of the period. So this is going to be 3 pi over 2. Here we'll break that into half, into half again. So this is negative pi, this is negative 2 pi, so this is negative 1 pi, this will be negative pi over 2, this will be negative 3 pi over 2. Okay. There's no x shift, so my 0 point is going to go there, and my period is 2 pi, so I'm going to get a vertical asymptote every pi units, I'll go negative pi and positive pi over 2. That should be pi over 2 right here. So from here to here is pi. That's the distance between the vertical asymptotes. So put 1 here, and then I'll get my cloner on here. So I'll put 1 here. That's pi units. Pi units. Go the other way. Pi units. And we could put 1 over here, about right there. Do the same thing all the way over here. Just about to go off the screen. Okay. Between vertical asymptotes, zeros. So all these points are the x-intercepts. Now it's going to go the opposite way we went here, because this was reflected across the y-axis. But the thing is, what this 2 does is, instead of having this guide point at +1 and -1, it's going to be at +2 and -2. So this is 2, this is -2. So we go halfway between up 2, halfway between down 2, halfway between down 2, halfway between up 2. And this one goes down, this one goes up. And so when you draw these in, this thing's going to be, it's going to be stretched out. This is a vertical stretch. Like that. So what I'm going to do is I'm going to plot both of these. The parent function, which is just the tangent of x, and then the tangent of 2x. So the red is the tangent of x, and the blue is 2 times the tangent of x. So we go here to 0. Well, let's change the, we're going from negative 2 pi to positive 2 pi. So there we are, right in the middle. So the vertical asymptote is at pi over 4 and negative pi over 4. And got a problem here. Let's look at something going on here. Oh, that's the problem. It's 2 times the tangent of x, not tangent of 2x. Okay, so there we go. That makes more sense. So we got vertical asymptote at pi over 2 and negative pi over 2, which gives you, between asymptote it's pi, period is 2 pi. So normally you would go over 1, well, you go over halfway between the intercept and the vertical asymptote, which would occur there, which is this point. Then you would normally go up 1 unit. Now you see we're going up 2 units, and so that the blue curve is vertically stretched, but it still has the same vertical asymptotes. And that was reflected in these points here compared to those points down there. Okay, so we've done changing the period, done y-axis reflection. We've done a vertical stretch. So the next one would be if we have a negative sign. Say, let's just do the same one we just did, but put it -2. See what that affects. And I'll draw it on this diagram over here. So you have negative tangent of 2x. This negative sign here is at the x-axis reflection. So if I go down to this graph, what happens is that I take this 2 tangent of x and I reflect it across the x-axis. So this positive 2 becomes a negative 2. This negative 2 becomes positive 2, and it happens everywhere. So what happens is it actually is the same. The negative, the x-axis reflection and the y-axis reflection end up with the same result, because the x-axis flips it over here, and the y-axis flips it here, and the x-axis flips there. Because of the symmetry of it, it ends up being the same result. So that's how you would do the x-axis reflection. Okay. Now we've got the x-axis shift. So this is, we had A and B. The shift is B divided by A, which in this case is because A is 1, B is going to be pi over 2. B over A is pi over 2. So what we have is an x shift of pi over 2 compared to the parent function. So the way we reflect this is to shift the vertical asymptotes and the x-intercepts that much. So let's do it here from 0. The period is going to be, because it's just 1, the period is going to be 2 pi. So if we want to do 2 full periods, we're going to do 2 pi and 4 pi. And then we break that up to halves. So this will be pi, 2 pi, 3 pi. Then quarters, this will be pi over 2, pi, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2. Okay. Now normally, for the tangent function, we have vertical asymptotes of negative pi over 2 and positive pi over 2. But when you shift pi over 2 units in the right to the right, everything's going to get shifted. So instead of being a pi over 2, it's going to be a pi. So this goes to there, goes to there. Oops, I thought I had an infinite cloner there, but I guess not. Let's try that again. Infinite cloner, that's what I need. Okay. So those are the vertical asymptotes. Now, they've been shifted pi over 2 to the right. Halfway between, you have zeros. So once you get the vertical asymptotes, the x-intercepts are just symmetric between the two. Likewise, we would go over 1 and up 1, because this is the amplitude here is 1, so we're not going to have any vertical stretching. So here's some marks. This is 1, 2, 3, negative 1, negative 2, negative 3. So we go halfway between the x-intercept and the vertical asymptote. We go 1, halfway down 1, halfway up 1, halfway down 1, halfway down 1, halfway up 1. Just following. I think I might have done these a little too low. And then you can draw your function in like this. So that's how you handle x-axis shifts. You shift the vertical asymptotes and then do everything kind of relative to those vertical asymptotes. The x-intercept's halfway in between. Then halfway between the x-intercept and the vertical asymptotes, you go plus or minus 1. And then finally, the y-axis. So if you had tangent of x plus 1, you just take these points. So you still have the same vertical asymptotes. You're just going to move these points vertically. And let me just to make it easier, so we can let's duplicate what we had. So we're leaving this part the same as the previous problem, and then we're adding one to it. So what you would do is you'd come over here, because you know, the asymptotes are shifted the same amount, the period is the same. What I would do is for this one, I'd move this point up 1, and I'd move that point up 1, and I'd move this point up 1. And you do that for all of the points, all 3 of the points. So now what you have is the kind of the midpoint of this trig function, where it has the same symmetry on either side, would be shifted up 1 unit like that. So this is move up 1, this move up 1, this move up 1. And likewise, this moved up 1, this moved, this is up 1, so it goes 2. This will be, is it negative 1, so it moved up to 0. So it kind of looks like that. So that's how you handle vertical shifts. And then you put it all together if you want to do a more complicated one. So let's do 2 that have at least a few parts to it. We won't go as complicated as we could. So let's say we have the tangent of 2x minus pi over 2. So I've got this number is other than something other than, you know, it's 2. Let's say this is 2 pi x minus pi over 2. So what we would do here is we would factor out the 2 pi. So you get 2 pi times x minus, so we factored out 2 pi, we're going to we're going to take pi over 2 and divide by 2 pi. So we take the reciprocal of the denominator. Pi's cancel out, and we get 1 over 4, so it's 1/4. So that's 1/4 of the unit. And that's the form that we want to use. So what is this telling us? Well, this number we can get the period from. So it's 2 pi over 2 pi, which is 1. So that's the period. The x shift is plus 1/4. So it's not plus pi over 2, it's plus 1/4. Okay, so how do we reflect both of these things? So we have no reflections involved here. So everything, we are going to have a shift. The first thing to do is to draw the axes. We'll do it where it's symmetric around the y-axis, about the origin. So you see the period is 1, so that means we're going to go plus 1 and minus 1. Let's go ahead and put some marks here. So you can see the scales are offset. They're not the same. Okay, so we go half period, so that's a half. Fourth, so it's 1/4, 2/4, 3/4. And then we have the same thing on the negative side. So we have -1/4, -1/2, -3/4. Now, the vertical asymptotes are half periods, so we're going to have a vertical asymptote every half of a unit. So this is 1 full unit, so we're going to have vertical asymptotes this distance apart. But remember, if I plug in x equals 0 here, without this shift, I'm going to well, yeah, let's take this into account first. So, you know, without the x shift, we'd have the origin here. But what's going to happen is we're going to shift everything a quarter of a unit, including the vertical asymptotes. So, you know, the standard vertical asymptotes would be here and here without the x shift. So now they're going to move a quarter of a period in the same direction. And the vertical asymptotes are spaced half a period apart. So those are the vertical asymptotes. In between the vertical asymptotes, you have the x-intercepts. And then we can do our normal thing. We don't have a constant out here other than 1, so we're not going to stretch it in the vertical direction. So we can go halfway between the intercept and the vertical asymptote, put 1, halfway, -1, halfway, +1, halfway to the left, -1. You just keep doing that for each one. Like that, and then we can draw our standard looking shape parabola curve. Okay, so let's plot that. So we want to go from -1 to +1. -1, +1. The function is the tangent of 2 pi x minus pi, what was it? Minus pi over 2. 2 pi x pi over 2. And we plot that. And there we see it. So you can see I go from vertical asymptote at 0 to another vertical asymptote at pi over Oh, I got it, yeah, wrong. I got to put it in units, non-pi units here. So you go from 0 to 0.5. So let's see if that's true. So you go from 0 to 0.5. And then you have another vertical asymptote at 1. Another vertical asymptote here at 1. Notice if I draw my vertical asymptotes here, 0.5, go halfway between 0.5 and 0.25. The function is going to be equal to 1, and if I go the other direction from the x-intercept, it's going to be -1. And then it just repeats, so you can see that that is what I got. Okay, let's do one more, last one as an example here in the lecture. Let's say it's -3 tangent of 4x plus pi over 8. Okay, I think that'll work out. So we've got an x-axis reflection, we've got an amplitude thing, our period's not equal to 2 pi, and there's a shift. So let's start off with the period. Period is equal to 2 pi divided by 4. So that's pi over 2. Now, I just noticed I have to get this in the form where, and I may want to change my number here. I don't want this to get too crazy. So remember, what you do is you take this and divide by that. So that's, well, I guess it'll work out okay. So if I factor out a 4, we'll get 4 times x plus pi over 32. So if we divide by 4, we'll get pi over 8 divided by 4, which is pi over 32. So what I've got here is my amplitude is, my period is 2 pi. My x shift is minus pi over 32. This is my amplitude. So what that means is I'm going to change these points, the non-intercept, vertical asymptote. And this one is going to be an x-axis reflection. Okay. So I'm going to go 2 periods to the right. So the period is pi over 2. So this would be pi over 2. And double that would be pi. So that's 2 periods. And I break that in half and I get pi over 4. And I get pi over 8. Here I get 1 pi, 2 pi, 1/8, 2/8, 3/8, 4/8, 5/8, 5 pi over 8, 6 pi over 8, which would be 3 pi over 4, 7 pi over 8. Okay, so that's that. Now, normally I would have the vertical asymptotes, so I'm going to draw one in here. It would be at plus or minus a quarter period. But you'll have asymptotes every quarter of a period. It's half the total period of the function. So that would normally, I normally have one here at this point, and then I go 2 of these marks and put a vertical thing. But what happens is I'm going to move this minus pi over 32. So that's going to be moving it about a quarter of the way, because if this is an eighth, then a quarter of the way would be here. So a quarter of the way, then half, 3/4 total. So the vertical asymptotes are going to be there. So you can see I go 1 mark, 2 marks, 1 mark, 2 marks. Go 1 mark, 2 marks. Finally, so what I'm doing here is I'm crossing this 1 mark, going full mark, and then going 3/4. Okay, so those are my vertical asymptotes. So I've taken into account the spacing of these from this number. I've shifted my vertical asymptotes by this number. Now normally I would, so the midpoints of these are going to be right there, right there, right there, right there. So those are the midpoints between the vertical asymptotes. And normally I would go over 1, or halfway between the x-intercept and the vertical asymptote. I go 1 unit. So let me put some marks on here. So this would be 1, 2, 3, 4. -1, -2, -3, -4. Okay. So normally I would go halfway between the 0 and the vertical asymptote, and I would go up 1. But the 3 says I'm going to go up 3, but the negative sign means that I have to reflect it over here. Normally I would go halfway between the green and the red, and I would go down 1, but I'm going to go down 3, and then I'm going to reflect it. And once you get one of these done, you can just kind of put all the other points in there. They're all going to be the same. So I'm just cloning those points, and the same thing here. These points are going to be down there. And then once you have that figured out, you can draw them in. And then, like I said, once you have one right, you get them all right. So this 3 here stretches things out in the vertical direction. So what I'm going to do is I'm going to go from 0 to pi. So change the go to 0 to pi. Let's go from -4 to +4. That kind of matches my scale a little bit. And then we have -3 tangent of, was it 4x minus pi divided by 8. Graph that. So let's see, how does that look? So there you go. Has that shape? That's the right shape. And you can see here, if I go the vertical asymptote, let's put these in terms of pi. So it looks like the vertical asymptote is going to be somewhere right between these two. And then if you go halfway between the vertical asymptote is going to be right between the center point of these two. So the vertical asymptote is going to be right there. And then if you go halfway between that point and this point, you're going to end up there, and the y value should be around 3, -3. You see about part of one, 3 whole ones, and part of the other one. So here, I didn't show this. You got this one, half of one, 3 full periods, plus half of the last one, if you go to pi. Okay, so that is it. And so give it a shot. Give the homework a shot.